So we can ignore the top line for the moment, but our bottom line, we're taking HCN, we react it with H2O. That's going to produce our CN minus and H3O plus. Okay, a potentially throwaway comment was dropped by one of your classmates saying, oh, dots and lines, we've got to worry about dots and lines. No, I don't think you're actually going to have to worry about that. That's going to, again, come down to how Dr. Schneblin formats her quizzes, but I'd be surprised if she's going to push too much on structure on you. What you're going to see instead is the formulas. Why is that structure provided? The structure is provided to give you some context of what's happening within this. When we're talking about acid-base reactions, what she's trying to do is provide a broader context to realize that when we're looking at chemistry, it isn't formulas that react, it's compounds. Those compounds are made up of bonds and technically lone pairs and atoms, and we should have some underlying understanding of what our symbols and notations mean. Okay? So if we're going to look at that bottom one, we're taking HCN. We're assuming it acts as an acid. How do we know it acts as an acid? What's that? It tells us, yes. Okay? And that may sound like kind of a stupid statement. That is not a stupid statement. That is exactly what you should be using as you navigate through these questions. Okay? So leverage that information to decide what it means. Okay, if it's going to act as an acid, what does that mean? It donates H plus to water. So what happens is the HCN structure loses the hydrogen. We no longer see the hydrogen connected to it. Okay, and then the hydrogen's connected over to our water. Okay, the important parts to note within this, less so the structure or even the dots, the important part to note is that because we started neutral and we got rid of H plus, we're becoming negatively charged. If we were going to leverage in our structural information, that's where we would actually see the dots starting to appear. Because if we're going to get rid of H plus, this hydrogen was connected to our carbon through that blue line. That blue line represented 2 electrons. If H plus comes off, it's coming off with no electrons. Those blue electrons would then remain with the carbon, which is why we would see that lone pair now appear on our carbon. Kind of, sort of? Okay. What happens with the water when it gains that hydrogen? Well, since it's gaining H positive, since it started neutral, it's going to become positively charged at the end. Kind of, sort of? Labels that we could go through and drop in. We were told the HCN is acting as an acid, which then means the water is acting as a base. Since we're now moving our focus over towards our products are going to be our conjugates. The question becomes, conjugate what? To determine what that extra conjugate is, what we're trying to do is think about what happens if we ran the reverse reaction. So for H3O plus to become H2O, what did the H3O plus have to act as? It had to act as an acid. It had to lose that hydrogen. So we're referring to the H3O plus as the conjugate acid. If it's the conjugate acid, what must the CN minus be? It must be the conjugate base, which we could equally prove by looking at how it relates back to the HCN. What did it have to do? To go from CN minus to HCN, what did it do? It gained H plus, okay, which is the definition of a base. Yes, sir. I'm a little nervous or leery to answer that question because I would say the conjugate is always the products. But my understanding is the definition is much broader than that, and conjugate can refer to both sides of the equation. Okay, I think that's a horrible way to reference it, but Alex may be referencing it based off the truest sense of the definition, so you may encounter that as an issue within Alex.
So is it kind of just like where you started with?
Yeah. So the point is to provide clarity onto which side of the equation you're looking at. Conjugate partners, you will always have two conjugate partners because you've got the acid with its conjugate base, and you have the base with its conjugate acid. So if you're being asked for conjugate partners, you're going to be referring to two things, both the base and the conjugate acid, or the acid and the conjugate base. Make sense? Okay. So we've got all our labels on it. The reaction we've got shown above, so now let's bring that back in. That reaction shown above happened where? That was on the previous slide. That was the slide we ended lecture on Tuesday with. So that's review content. It's doing the same kind of thing. We're still running an acid-base reaction. We still produce the H3O+. If I lined everything correctly, all of our labels would still come out to be the same. Why am I including it up there? What we're going to start to move into is now understanding something potentially about the danger, quote unquote, of these individual acids. So if we think, here's a vat of acid, are you okay sticking your hand in it? I say, here's a vat of acid. Are you willing to stick your hand in it? Probably not. You're not willing to drink it. Never, no how, no way. We would never do that. Have you had a soda lately? Guess what's in the soda? Carbonic acid. Right? And you're drinking that like no tomorrow. Well, what the hell? Okay? So that's okay to drink, but not just this random vat of acid that we're talking about. Right? So there's a context that also has to be brought into play when we're talking about these acids. And one of those words that'll come up is our strength. Okay? And what that strength is ultimately dictated based off of is what is the reactive thing when we're talking about our acids. The reactive thing is the ability to give up that H+. So we're thinking about H3O+ as being our dangerous thing. Right? So if I have lots of H3O+, that's now a dangerous thing. Okay, why does that become important to us? Well, if we talk about H3O+, how many times had you heard about H3O+ prior to 2 years ago? You probably never heard of it. Okay? And it's the concentration, it's the amount of it that's important. How often had you even heard about concentrations prior to 2 or 3 years ago? You might have heard of them a little bit more, but probably equally not very much. This starts to produce a problem, because if we talk about acids, had you heard about acids prior to 2 or 3 years ago? You probably had some context that they were dangerous, so we didn't want to touch them. So you knew that information, and yet you didn't understand any of the reasons or the logic behind it. Right? And that, I would argue, was actually a careful choice made by scientists who studied these different chemicals to provide some kind of safety context. Right? That safety context is giving us information that allows us to be aware of it without having to dig into dealing with H3O+, or dig into the concentrations, or heaven forbid, dig into the powers of 10 that are typically associated with our concentrations. Right? So scientists had to look at this and say, is there another way that we could repackage this so that we can sell to the common populace some minimal amount of safety without having them to learn a whole bunch of stuff? Prior to 2 years ago, had you heard of pH? Ooh, interesting. You know what pH is? What is pH? Whether something is acidic or basic. It's giving us some information about that acid characteristic and that basic characteristic. Right? And we've theoretically grown to learn that low pHs and bad pHs, or high pHs, are bad, and that middle pH was good. Okay? What does that mean? What does it mean to be a low pH or a high pH? What the hell even is pH? Okay? pH was scientists taking a look at this H+ concentration and saying, again, how can I repackage this so that I can sell it to people in a minimal education level? So what was it? That's pH. pH is saying H3O plus, the concentration of our hydrogen ion or our hydronium ion, however you want to look at it, is a dangerous thing. And if it's really concentrated, it becomes dangerous. And if we flip that and look at the hydroxide, it becomes really dangerous. So we want to take away some of that scientific knowledge. We want to get rid of concentration. We want to get rid of really even the identity of that species. Okay? When we say acid, you didn't necessarily know that that meant H3O+. When we say base, we don't necessarily know that that was hydroxide. And we don't have to translate that information. We just have to ensure that people acknowledge at either end of those spectrums, it's bad. Okay? So what we went through and did is said, hey, mathematicians, we've got this weird, goofy number that we want people to understand some level of safety about, but this number is so complex, people are going to screw it up and not be able to interpret it correctly. Give us a mathematical operation that changes the number into something that people can deal with. And mathematicians come back and say, take the negative log. What the hell does that do? You take the negative log of your hydrogen concentration and it drops you into a scale of 0 to 14. Instead of dealing with powers of 10 and weird decimals, you've got 0 to 14, which is a lovely system because between 0 and 14, we have enough fingers and toes that we could count that number scale. That's phenomenal. That allows us to wrap our puny human brains around this concept. And if we now start to go through and map out that content, we can recognize that water comes in at a 7. That's neutral. 7 is good. That's safe. But if we're dropping down to a 1 or a 0, that's really bad. And we've now provided some context that allows the common populace to be able to recognize something about the hazards of a particular chemical. That's pretty phenomenal. And we now have it effectively as a number scale. Okay? You are now chemists, you're now those scientists, which means you have to take that common knowledge stuff and you have to convert it back to something that you can use. So you're going to have to do the anti-log because you need to get back to concentrations. Why concentrations? Well, we deal with equilibrium expressions. And what shows up in the equilibrium expression? Concentrations. Okay? So you're now dealing with pHs. How do you take that concentration of H plus that you've worked with, and how do you spin that into a pH? Well, you take the negative log. Punch the buttons into your calculator, ta-da, spits out a number. How do you take a pH and turn it into your concentration of H plus? Say again?
Regular log or natural log?
Okay, what we would do is the anti-log. Okay, so this now pushes to mathematics, and what's the anti-log? Powers of 10. Okay, so if I want to know the concentration of H plus, what I would do is take 10 to the negative pH. Okay. That power of 10 undoes the log, so I take the power of 10 to both sides, technically. 10 to the negative log undoes that, brings the negative around, and we've got everything kind of shifted out to where we now get the concentration of H plus, the log and the power of 10 cancel, and we get the concentration of H plus is now 10 to the negative pH. Relatively simple conversion. It allows us to manipulate back and forth. Why is this special to the previous slide where we're talking about those two different acids? Well, one of those acids produces more H plus. We would see that when we ran the pH, or when we tested the pH, or if we tested for those concentrations. Kind of, sort of? Okay. One of the kind of interesting points within this scale, or within this pH system, is that it's really all centered on water. Why do we pick water as our central point? Why is it? Well, we don't even have to get into why it's neutral yet. Where's water? everywhere. Okay? That's our default. And not only is it everywhere, it's generally considered as safe. That's a good neutral point to have. We now have something that is ubiquitous everywhere around us and generally considered to be safe, at least as far as contact exposure. Let's ignore the drowning hazards. Okay? Kind of makes sense? So if we push into water, why would we look at water? Well, number one, it is our general solvent. But if we go through and look at how water reacts and responds, it has an interesting observation that if I mix water with water, kind of like if we mix an acid with water or a base with water, what happens? Well, what do we produce when we mix water with water? We get hydroxide. Ooh, that sounds like a base. And H3O plus. Ooh, that sounds like an acid. So water is actually the dead center for us as far as the acid-base definition. Okay? Which again goes all the way back to our initial definition systems. It was based on going into water. Okay? So water is our perfect kind of neutral point that allows us to navigate this. Okay? So now let's push on it even further. Is this a product-favored or reactant-favored equilibrium? Do I expect more water in water, or do I expect more hydroxide and hydronium? It is product or reactant. Yes, it's one of those. Which one do you think it is? Why is it reactant favored? Just because there's two of the same reactants doesn't necessarily change anything. Do you know the concentration of hydroxide or hydronium in neutral water? You're like, no, I don't. Do you know the pH of hydronium in neutral water? You're like, no, I don't. Come on. That was on the slide. Do we know the pH of neutral water? Yeah, it was 7. Okay? That was something theoretically you already had trained. And by flipping back to this, I gave away some of the answer, but we can hide it. Okay? If we knew that the H plus concentration in water, our pH was 7, can we calculate the H3O plus concentration? Yeah. The H3O plus is going to be equal to 10 to the negative 7th. Where did the H3O plus come from? Where did I get this H3O plus from? Yeah, from the H2O. And in the process of producing that H3O plus, what else did I produce? OH minus. So do I know the concentration of OH minus? Yeah, what's the concentration of OH minus? And if I'm being asked about is this product favored or reactant favored at equilibrium, in particular, what am I asking about? What is the size of K? Well, how do I calculate K? Products over reactants. What are our products? The OH minus concentration and the H3O plus concentration. Over our reactants. What are our reactants? H2O. Okay, which I could go through and write twice, but I'm not going to write it twice. Why? I'm not even going to square it. It's not just one. It's a liquid. And because it's a liquid, what is happening to the concentration of the H2O? It doesn't change. And because it doesn't change, it's a constant. I can group that constant and fold it into my K value, and I just have a new K value. Which then means, what's my equilibrium? K equals hydroxide times H3O plus. What was the concentration of hydroxide? 10 to the negative 7. What was the H plus? 10 to the negative 7, which means my K is 10 to the negative 14. Is that a big K or a small K? That's a small K, which means the reaction is reactant favored. All of that stacks in. You're pulling up all of that content from the previous unit. Okay? Remember, our last lecture on Tuesday was, guess what we're just going to do for this entire unit? We're just going to talk about the last unit with specifics to acid-base chemistry. Okay? So it's a rehash. All of this is now redundant material. This K is now so special. Why is it a special K? This is the K referring to what chemical reaction? The reaction of water. Why would that be a special K? Where is water? Special K. Sorry. Why is the K for water a big deal? Where is water? It's in your breath. It's in your body. It's in the materials you're drinking. Water is everywhere. It is such a common species to be aware of that we might go through and emphasize the fact that this K is so important that we don't call it just a K. We call it a KW. KW for water. Yes, because water begins with a W. Again, creativity in scientific naming. Okay? So, pure water contains small amounts of our H3O plus and our OH minus. Okay? For neutral water, we just calculated it based off of knowing the pH. Comes in at 10 to the negative 7, which sets us up with our KW of K14. Negative 10 to the negative 14. Kind of, sort of? Cool. Okay, which then takes us to our pH scale again. We've got a new version of it that's much less colorful. You see references of red and blue. Why? Because the materials, the pH strips that we use to detect acids and bases naturally change from red to blue. Okay, so the scale that's being shown here is because of the techniques or the instruments we're using to actually detect them. Okay? Which then sets up a big old nasty system at the bottom of a whole crap ton of equations. Okay? We just talked about the pH. We know pH is negative log of H3O plus, which means we know H3O or the H3O plus concentration, or 10 to the negative pH. We know the KW. Okay? Because it's 0 to 14, we know the pH plus the POH is 14. What the hell's the POH? What did P mean? P means negative log. So I can take the P of anything, which just sounds fun to say. Right? So I can take the P of the H plus concentration, or my hydronium ion. I can take the P of my hydroxide ion concentration. It's all just going to depend on what I decide to look at. If I decide to look at the hydroxide concentration, I'll just take the negative log of that. Ta-da! I've got a POH now. And because we're talking about water, we're confined to this 14, which then means the pH plus the POH has to equal 14. Which then also means we get this POH, which then also means I can get the hydroxide ion concentration. And now all of these things become equations for you to be able to interconvert between. Hooray, don't we love equations? Right? So you can be given pretty much any one of these pieces of information and be asked to solve for any one of the others. Kind of, sort of? Let's take, because I don't remember if we talk about it later or not, let's take a quick look at that KW, 10 to the negative 14. What affects K? Say again? Does concentration affect K? So if I increase the concentration of H plus, what has to happen to the concentration of OH minus? It has to decrease, which means what happens to K? Stays the same. So concentration actually has no effect on K. Concentration will affect my interpretation. It means I'd be Q, not K. And then I would navigate to making it K. Right, but concentration doesn't affect K. What does affect K? pH. What is pH? pH is just a fancy way of looking at concentration. What affects K? Okay, and we'll take a pause here within this because this is an important question. This is a question that was actually asked on quiz 2. So if you go back and look through quiz 2, there was a very particular question that asks what happened to K during the course of something. And the answer was, good job, nothing. Yeah, it was silence. Okay? Because in the course of that question, all you changed was concentrations, and the concentrations don't affect K. What affects K? Volume is ultimately just changing the concentration. What affects K? It's getting hot in here. There it is. Temperature is what affects K. So when we're saying Kw is 10 to the minus 14, there's an implied piece of information running with that. That implied information is saying temperature. This is temperature at what? Sorry, that was phrased horribly. This Kw equals 10 to the negative 14th at what temperature? Room temperature. And why would we pick room temperature? That's where we're going to deal with our chemical reactions most frequently. So it makes sense to pick a standard temperature. Clearly it's not standard, but to pick a temperature that is most representative of all of the reactions that we would go through and use. Right? If we change the temperature, that's going to change the value of K. And if K changes, what happens to the concentrations of H plus and OH minus at equilibrium? They will also change. How will they change? That's going to be dependent on which way you moved the temperature and all of that fun stuff that you could stack in from the past unit. Hooray! So, soda has a pH of about 2.5. What are the concentrations of H3O plus and OH minus? Is this solution acidic or basic? And then if we're going to compare it to orange juice at a pH of 3.5, how many times lower is the concentration of H3O plus compared to the soda? These are blue boxes, which means words from your face. Since you all stopped talking, I'm going to assume you all figured it all out. Right? So solving for the H plus concentration should be relatively straightforward. pH equals negative log H3O plus. We can do the anti-log, and we get 3.16 times 10 to the negative 3. Okay. Technically, moles per liter and all that fun stuff. Okay. Which is odd coming from me, considering that ranted and raved about showing units. How do we get the concentration of the hydroxide? Okay, well, we know the pH plus the pOH equals 14 because why? We're in water. Since we're in water, we know that is true. So I can then go through and say that the pOH is equal to 14 minus the pH. And then I can go through and say that the OH concentration is going to be equal to 10 to the negative 14 minus my, what was it, 2.5? Yeah. 2.5, and I can go through and get a number. What number did we get? 9 something? Oh, okay, well. Negative 12. I may be thinking of different numbers. Kind of makes sense? Aye. Is the solution acidic or basic? acidic. How do we know it's acidic? Because we've memorized that pH scale and we're under 7, so it's acidic. Make it harder. How else do we know it's acidic? The concentration of the H3O plus is greater than the concentration of OH minus. Okay? So multiple ways that you could go through and manipulate it. I would have argued we would know it was acidic right out of the gate by looking at the pH, but we could just as equally look at the concentrations, which is why that question followed second, not first. Kind of make sense? What happens when we look at the bottom? Okay, if the pH of orange juice is 3.5, how many times lower is the concentration of H3O plus? Okay, I want to lean into that a little bit. What happened to the pH? It increased. What happened to my concentration of H plus? So we could just be like it lowered, okay, if we were going to do that, or we could conjugate it and be like it decreased. So an increase in pH meant a decrease in H plus. You mean they're inverses? Yeah. Why are they inverses? Because of that negative sign. That negative sign that I've told you in past units we're going to have to watch out for. The negative sign will come in and mess with your interpretations. You got to be real careful to pay attention to it. That negative sign is what's causing our inverse relationship. Okay, so you're going to need to make sure you track that as you navigate through this. Or you cheat and have it written down for you. All right? So if we look at the pH difference, what happened? Our change in pH, 3.5 minus 2.5, the difference is 1. So the orange juice is 1 times lower the concentration of H plus. But wait, if it's 1 times lower, wouldn't it be the exact same concentration? Because that's what happens when you multiply something by 1. That doesn't make any sense. Say it again. It's 10. The difference here is 1, but that's based off of what scale? The negative log scale. Excuse me. So what we would have to do is take that difference and convert it into a normal scale to look at H plus versus OH minus, okay, which means you have to deal with that power of 10. We're looking at a 10 times lower concentration. Okay? Make sense? Okay. So Ka is the equilibrium constant for an acid reacting with water. We got a blue box. Write the equilibrium constant expression for the Ka for this reaction. I'm going to throw some more shade. All right, it's too sunny in this cramped up room. Okay. Do you have that written yet? I gave you twice as long as I took to write it out. At least twice as long. If you don't have that written yet, why not? I was busy writing the equation. The equation that you already had in your notes, because you have the slides. I was too busy writing the question that you already have in the slides. You're writing redundant information that's slowing you down, which slows the entire progress of the class down. Because now what's happening is I'm not waiting for you. We write the answer, and you're like, oh, ta-da, there's the answer. It's obvious. Of course the answer is freaking obvious. It's the answer. That's the point of the answer. Right? Pay attention to what you're writing down in your notes. You should be picking up and attempting questions right away, not providing the context of the question. Okay? It can be helpful if we had slide numbers. I can put slide numbers into the slide deck so that we see the numbers on it. So you could be slide 4. This is the answer to the question that's being asked. Make sense? Okay, so cool. There's our K expression. Why would we call this a Ka and not just a K? Why do we call it Ka and not just K? How do we know it's an acid? It tells us something else. How do we know we're looking at a Ka expression here and not just a K? There it is. We see the presence of H3O+. H3O+ is our tip-off that it's an acid. If we had this K expression, could we backtrack what the actual equation was? Because how do we calculate K? It's products over reactants, which means Cn minus and H3O+ are the products. Ta-da. Reactant, HCN, ta-da. Boom. We've got our equation. You didn't need to write any of that other stuff down. Okay? Recognize where that information is coming from and how to manipulate and get to our questions and answers more efficiently. Okay? One of the neat things of our equilibrium expressions for acids and why we also tend to study these equilibrium reactions and not other equilibrium reactions, they're stupid fast. Okay? If we were going to try and study the K for human decomposition, okay, that's going to be an experiment that's going to suck. Why is that going to suck? You're going to have to wait a lifetime for the person to, number one, stop living, and then you've got to wait for them to continue to decay. Right? That's going to take a really long time to study. And how long do you have to study? 2 hours and 40 minutes. That's how long you get in the lab. Right? We don't have a fast forward button. So what we want to do is look at reactions that allow us to study these concepts as efficiently as possible so we can pull that pretty quickly with our acids and bases. Oops. Okay. Table of a bunch of different acids. What do you notice about the pH of different 1 molar acid solutions? This is a blue box. So you should be talking at your table. What do you notice? Go through and look at the columns within the table, look at the acids, look at all the stuff. Tell me what you see. Or tell your people at your table what you see. So cool. What do we see happen to the pH? Okay. pH from top to bottom did what? It increased. Cool. Top to bottom, we're showing that increase. Okay, so we just, the pH increased. That's kind of silly. But, well, go beyond. What happened to the H3O+ concentration? Okay, so depending on how we wanted to format our interpretation on this, admittedly, yesterday I formatted it slightly different. I would argue we should maintain our labeling system. Okay, and what happened? We see an increase in concentration of H+ as we go up. The pH increased going down the table. Ooh, they were opposites of each other. Why were they opposites of each other? The negative log. It was that mathematical operation that's messing with our interpretations, which means we have to be real careful to interpret our pH or H+ concentrations correctly. Okay? Particularly with a really straightforward question of, the H+ concentration increased. What happened to the pH? Okay? Nailing that directionality can be really challenging, particularly in a question that looks really short and straightforward because it's doing the inverse of what we would anticipate with increases versus decreases. Kind of, sort of? What happened to the Ka? Decreased going which direction? Because I'm not very good with powers of 10. Whoop. We maintain our arrows. Okay, it increased going up this table. Okay, or it decreased going down, perfectly valid. Okay? So again, we've got these swaps back and forth with the increase versus decreases. We have to make sure we're really careful with those interpretations. Okay? Does this give us some secondary information? If I have a vat of hydrochloric acid and a vat of hydrocyanic acid, secondary issues, okay? Which one, if you're forced to stick your hand in, should you stick your hand in? Hydrocyanic. Why? it's not producing as much acid. Kind of makes sense?
How's their pH at 0? I thought it was from 1 to 14.
It's 0 to 14. And even then, we run into weird kind of sketchy floatiness on that, but it's technically 0 to 14. Right? So we say, oh, I want to avoid HCl at all costs. HCl is going to be dangerous. That's going to melt my hand off. Right? But there's an important aspect that we have to be real careful within the phrasing of this question. What was held constant? True, temperature was held constant. We didn't mention temperature. We actually mentioned something that was held constant. The concentration of the initial species. What happens if I start changing the concentrations? Let's say I have a 0.1 molar concentration of hydrochloric acid versus I can't do this, but we'll just say for the hell of it, 100 molar concentration of hydrocyanic acid. Does that change which vat we want to stick our hand in? I mean, we don't want to do it, but... Okay. Why should that change it? If we're at 0.1 molar, I'm only going to get 0.1 molar H plus coming out of it. If I shift to the 100 molar, that's now going to significantly change the concentration of the acid. Okay? Admittedly here, if you're dealing with numbers and you can manipulate those numbers that well, okay, maybe you'll say, oh, it doesn't change it. Okay, but what you should be thinking about is the concentration of our initial acid can greatly affect the H plus concentration. Okay, that's the bottom line. So just doing this based off of H plus can be a little bit dangerous with our initial interpretations because the H plus concentration can vary depending on what we're starting with. What would remain constant regardless of the concentrations we were starting with? The equilibrium constant. The equilibrium constant is always going to be constant because it's called a constant for a reason. Okay? So we could go through and we could evaluate the strength of the individual acids, hydrochloric versus hydrocyanic, and say hydrochloric acid is significantly stronger than hydrocyanic acid, not based off of the H plus concentration, but based off of its equilibrium expression, its Ka. So the Ka becomes a normalization factor that allows us to rank something about the individual strengths of those acids. Concentrations can then change kind of the output at the end, okay? But the strength is going to remain constant. Kind of, sort of? Ta-da, Thursday. We already did that one, so we're going to move on. All right, if we're talking about acids and bases can denature proteins. So remember I think that was our last unit. I think we talked about it within the equilibrium and thermodynamics. We looked at protein folding. Okay, that proteins were just this long chain of amino acids, and they would fold up on each other. They folded up on each other based off of intermolecular forces. Okay? The problem or good thing with acids and bases is acids and bases can react with those side chains on our proteins, and they can change the intermolecular forces. If the intermolecular forces change, what happens to the protein structure? It also changes. Okay? If that happens, we would go through and refer to it as a denatured protein. We've got the intact protein where it's all put together. If we break it apart, we get the denatured or unfolded protein. How is this happening? We've got kind of a nice little drawing down below. Admittedly, it's kind of grayed out, but if we take a look at the glutamic acid, we've got a negative charge there, and the lysine, we have a positive charge. Whoops. There's an attraction between that negative and positive. It's a pretty strong attraction because we're trying to neutralize those charges. If we add H plus into this situation, that H plus is going to change the O minus into OH. If it is OH, do I get the same strength of attraction? Nope. And if that strength of attraction changes, thermal temperature is enough that can cause the protein to unfold. And that's what we're seeing in the output on the other end. Okay. Similarly, if I add a base, the base could come through and remove a hydrogen from that nitrogen, nullifying the positive charge, and I would have a negative and a zero charge. Again, the interaction changes, and as long as the interaction changes, the protein unfolds. Okay? You can think about it kind of as Velcro, if you will. Okay? If we go through and start removing some of the Velcro loops, the Velcro becomes less strong. Okay? Acid-base chemistry is coming through and changing the state of your individual pieces of Velcro. Kind of, sort of? Okay. Bases have an extra special reaction that can run with them. Instead of just running acid-base chemistry, they can also go through a process known as saponification. Okay. This would be chemistry that would get discussed in a lot more detail in second semester organic chemistry. Okay. But the base can go through and react with fat molecules, and it can take that single fat molecule, this equation isn't balanced, and it can turn it into 4 parts. Why does this become a deal? Where do we see fat molecules? Be nice. Cell walls. Sorry, is that what you were about to say? Yeah, cool. Cell walls. Okay. Cell walls are made up of fat molecules. Okay, different forms of lipids. Okay, that's something you would learn in a biochemistry class. Okay, potentially 2 years from now. Okay, why is that a big deal? Well, if your cell wall loses its structural integrity, instead of being 1 unit, it's now 4 pieces. Those 4 pieces effectively float off, or are more likely to float off out of the cell wall, thereby creating a massive hole in your cell wall. Okay. Generally speaking, holes in walls defeats the purpose of the wall. Okay. And that's where you could get stuff floating out of the cell or stuff floating into the cell. Okay. Both of those occurrences could cause cellular damage. Okay. There's an extra little bonus that's kind of fun to talk about, so we'll mention it. This molecule, aggressively not correct for what we're talking about here, but has very interesting properties. That molecule is something that you have used, hopefully, every day of your life. Yeah, it's soap. Okay. Okay. If you go through and look up the structure of soap, soap is this. You have this very polar part of it, and then you have this very non-polar London dispersion, non-polar covalent tail. Why is that special? That hydrogen bonding ionic end interacts with water, and that non-polar covalent tail interacts with dirt and grease. So what happens is you squirt soap on your hands, rinse it with enough water, and build those bubbles. Those bubbles are effectively the non-polar portion grabbing and wrapping around grease molecules and then solubilizing them and allowing them to be washed off your skin. Okay? Go ahead.
Is that why a lot of soaps were historically made with animal fats in them?
That is why soap is very commonly made with animal fats. And how do you make soap? You take animal fats and you add lye. What is lye? Sodium hydroxide. Okay? Which also contributes to one of the more common expressions when we think, or not expressions, but observations that you would make for soap or base molecules. Basic molecules, if you rub them between your fingers, tend to be very slippery. Why? What's on your fingers? Cell walls, right? of your skin is a cell wall, and you're now rubbing the base on it, which means you're taking all the cell walls on your fingers and you're turning it into soap, which is why it's allowing it to slide around. Okay? So that slippery feeling is sometimes, when we talk about strong bases, the byproduct of you dissolving your hand away. Okay? Not particularly pleasant. Acids have a stickier feeling because they end up increasing the attraction between things that shouldn't be attracted to each other. So acids tend to have a sticky feeling, whereas bases tend to get a slippery feeling.
That's a terrifying thought.
Yeah, it is. For the record, don't let that stop you from washing your hands. Okay? Soap is still a good thing.
I was more concerned about the acid. Sticky.
Yeah. So, P or Ka, and now guess what do we get? A pKa. Why do we get a pKa? Well, Kas, if we looked at the values, okay, we can backtrack like 4 slides. If we think back to the values that we're getting for our Kas, what do we see in all of those? Powers of 10. Do we like powers of 10? No, we don't like powers of 10. So what do we want to do? We want to create a mathematical system that simplifies the powers of 10 into something that's more manageable to work with. Okay? We already did that with the H plus concentration, so why can't we do it for the Kas? We can. Okay? P meant negative log. So I can get a pH, I can get a POH, and I can get a pKa. All of those are falling under the same principles and the same patterns. So we can now look at a pKa. So we've got our acid reaction, we've got a Ka that can express it, and now we can do a pKa, which is now the negative log of that. Okay? If we go through and look at this, a Ka that is big, greater than 1, means what? Product favored. And if it's product favored, we would define that as a strong acid because we get lots of H3O+. If we had a Ka that was smaller than 1, that would be reactant favored. We don't get a lot of H3O+, which means we have a weak acid. That says reactant, just trust me. If we move over to the pKa, if we get a K that's larger than 1, when we look at the pKa, it's actually going to go negative. Okay? So a negative pKa is very, very, very strong. If we look at the Ka greater than 1, sorry, that's less than 1. Wow. Yeah, sorry, my brain. Okay, we'll get a positive pKa. So a positive pKa is weak, a negative pKa is strong. What does it mean if I have a bigger pKa? I'm not saying positive or negative, I'm just saying a bigger pKa. 2 things, and I have one of them has a bigger pKa. Okay? And this becomes the exact dilemma. It's a coin flip between weaker or stronger. And if you aren't careful with how you manipulate that system, you're going to end up getting it wrong. This is where this table can come into play and help you out. Okay? The bigger your value gets, the more positive it becomes, the weaker the acid. If you struggle with recognizing that, that is perfectly acceptable. I struggle with it all the time. Right? Which is why whenever I'm dealing with Kas or pKas or acids, I write out my K expression. I write out that acid base or that acid reaction. HA goes to A minus plus H3O plus. I write out my Ka, and I go through and say, well, what does it be? If I have a bigger this, how does that respond to the H3O plus concentration? And I have to derive it. And that's mostly because through my entire experience, how many cheat sheets was I allowed to have? 0. You're allowed to have a cheat sheet. So particularly for you, because you volunteered and volunteered incorrectly, this would be an awesome thing to have written down on your cheat sheet so that you don't have to think about it, because it is going to come down to a coin toss. And if it's written out for you, theoretically, that should simplify your interpretation and speed your interpretation along instead of having to derive it all the time. Kind of make sense? Okay. Examples, you could look at the examples on there. Okay. If you wanted to put those into your cheat sheet, I would argue those aren't going to be particularly useful from my perspective, but you could do it. Okay. The thing at the bottom becomes the really big important statement. The larger the Ka, the smaller the pKa, the stronger the acid. How important is that going to become? It's probably going to show up this semester. It shows up in OChem, it shows up in biochem. Do you need more chemistry? You're going to really need to know that expression, because in biochem, it's not a simple just let's compare these two things. It's let's look at 6 of these things and say, how does that manifest the structural representation? Okay? So you want to be super familiar with that last statement so that you can simplify your process later down the road. Kinda, sorta? Okay. So we can look at this kind of pictorially. A strong acid at equilibrium is product favored. So if we're taking HCl and we mix it with water, okay, what do we expect to have happen? Well, based off of its Ka and its pKa, these suggest strong acid. So the strong acid means products. If we look at my reaction, I would expect to see lots of H3O+. Okay, and lots of Cl-. And I should expect to see no HCl. So if we go up and look at my picture, I don't see a green ball next to a white ball because it was a strong acid. I would fully expect that to dissociate out, react fully out with my water. If we switch it up to a different acid, a pKa that's significantly larger, and a Ka that's significantly smaller, inverses, part we got to watch out for. What does that mean? That means I'm not producing as much product. Less product formation means I expect to see very little of the H3O+. There's only one floating around, and I expect to see a whole hell of a lot of the reactant floating around. What's the blue supposed to represent? All the different water molecules, so we didn't have to actually draw those all in. Kinda, sorta? Okay. So which is the stronger acid, formic acid or hydrocyanic? So we'll help with that. Right? If you got a table like this on the test, what I would highly recommend you do is start to cover things up, okay, or cross them out so that you know what things you want to look at. We want to compare formic acid to hydrocyanic. Which one's the stronger acid? Formic acid, okay. Why? Ka. So we could look at the size of the Ka. Should we be looking at the concentration of H3O+ or our OH-? Or sorry, not OH-, what is that? pH. Okay, no. Why not? Isn't that telling us the same thing? The pH gets lower for formic acid, so shouldn't it be a stronger acid? The H+ gets higher. Doesn't that tell us it's a stronger acid? It's only saying those things are present in a higher concentration. It's going to be heavily dependent on the starting concentrations. So if we reflect back to where this table came from the assumption that all of the solutions started at the same concentration. Okay? With that assumption, we're fine to look at the H+ and the O and the pH. Okay? But if we don't have that assumption within us or visible, we shouldn't be looking at the pH or the H+, because those are heavily dependent on our starting concentrations. The only thing that isn't dependent on one versus the other is the thing that normalizes the data and puts them all together into a single ratio known as the equilibrium constant, or our Ka expression. Make sense? How would we calculate the pKa? We just take the negative log. Negative log, make sure you got your parentheses around that, 1.8 times 10 to the negative 4, and it's going to spit out a number. Okay. Depending on what you're aiming for, you may want to be able to estimate that. I was always bad at being able to estimate that. But if you're doing like MCAT kind of preparation or potentially even DAT or PCAT, they may actually have you estimate your pH from H plus concentrations, okay, or your pKa from your Ka concentrations. Okay? Just be aware of that as a secondary issue. Why do you have to estimate it in those potential tests? Because they don't give you a calculator. Okay? Since you're allowed to use a calculator here, you don't need to estimate. You could just punch it into the calculator. Okay? But those particular tests do not allow the use of a calculator, which is why estimation becomes important. Make sense? Or at least they haven't in the past. So, strong acids have Kas larger than 1. Your pKas will be less than 0. So your strong acids will have pKas that are negative numbers. Okay? And I just realized I really don't like the organization of this table. Why might I not like the organization of the table? They're kind of like randomly placed in there. Okay? I would argue it would have been nice to start with the strongest acid and slowly get weaker. Okay? These become important acids to know. Okay? From my perspective, what you should know would be your chemical formulas for your strong acids. I personally think that's worth memorizing. Okay, because you'll see your strong acids, particularly if you're going to take more chemistry, show up time and time again. So if you have them memorized, you don't have to think as hard later on. If you don't need more chemistry, you don't need to memorize them. Your class in general doesn't need to memorize them because you have a cheat sheet. Okay? So you don't have to have that content memorized. Knowing the names, I'm kind of on the same page as Dr. Schneblin is with that. Like, who cares about naming things? We just look at structures. Okay. I would not recommend necessarily memorizing your Ka. I certainly wouldn't recommend memorizing your Kas because powers of 10, who wants to do that? Maybe pKas. So if you ever encountered me in OChem, I would drop the pKa for an acid every so often. Okay. Not a big deal for this class. It becomes potentially more important for an organic chemistry class. And even then, potentially more important. Okay. The primary reason we want to know that these are the strong acids is because every other acid that we will see will by definition then be a weak acid. Okay. And if we're looking at these as strong acids, their Ka value is so large that what is their effective reactant concentration? Remember, we look at a Ka. What's our reactant concentration if we get a Ka that's this large, 10 to the 10th? The reactant is really small. So small that what could we say about it? It's effectively 0. And we can ignore it when looking at a chemical reaction. So that then changes things, because if the reactant concentration is 0, am I at equilibrium? When do we look at equilibrium? When I have both reactant and product, because I'm producing both. Strong acids are so strong that we can approximate there being 0 reactant, which means none of it is ever being formed, which means these reactions or these strong acids are not equilibrium dependent, which means we don't need to stress about K values. We don't have to worry about all that equilibrium mumbo jumbo that we've been dealing with throughout the past unit. Strong acids shift our focus from 152 to 151 chemistry. 151 was unidirectional. We just make products. That's it. Why does that help us? Well, I can look at a problem now, and if the problem doesn't involve one of those things I've memorized, I have to worry about Ks. Right? So it can simplify how I go through and approach a problem, and it can speed me into problem solving without having to do a whole bunch more lookups. Kind of make sense? So why are strong acids strong and weak acids weak? A lot of it can come back to reviewing our content that we've already kind of addressed. We can go back and look at an energy diagram. For a strong acid, your product energy is really, really, really low. Your reactant energy is very, very high, which means that reaction is extremely exothermic. Did we already potentially know that? I would argue, yeah, because you all watch safety videos, right? You enjoy safety videos. Those are exciting things. And they show you that little demonstration about how you mix acid and water, right? How do you mix the acid in the water?
Acid first? No, wait. No, water for, no.
It's okay. Right? And this becomes the challenge for it. And I would argue that you'll never really memorize it, right? Because you never experience the failure of it. You add acid to water. So the acid goes on top into the water. Okay, why? You're going to generate that acid-base reaction, right, where the acid gives up the hydrogen to our water right at the surface. Why is that a big deal? Well, it's going to release some heat. As it releases that heat, it's going to heat up the surrounding environment, and it's just going to go straight up into the air. What if we flipped it the other way? We put the acid on the bottom and then water on the top. Now what happens? It releases some heat, but what's preventing the heat from dissipating? The water sitting on top of it, which then means it builds up that heat until it has enough kinetic energy to transition into the gas phase and push through all of the water holding it down, which ultimately means explosion. And we tend to not like explosions in the lab. Right? So that's actually one of the reasons why here you're seeing kind of the effect of why we need to add acid to water and not the other way around. When we look at the weak acids, we still tell you to do the same thing, add acid to water, but it becomes less of an issue. Okay? It's becoming less of an issue because that's an endothermic reaction. We aren't concerned about bubbling and boiling, but what we're concerned about is the habits of mind to ensure that you always add acid to water. Okay? So we can look at the energetic stability of the conjugate bases, right? And then you encounter this fun statement: the more stable the conjugate base, the stronger the acid. How do you know what makes stability? Do you care what makes stability? In this class, not really. Right? If you're going to move into organic chemistry, yeah, really, we're going to be concerned about it. What you're primarily concerned about are what are the numerics, okay, the quantitative data that tells you stability versus not. Those numerics are stored where? In the Ka expression. So it's the magnitude of that Ka value that's giving you all that information. You're using experimental data to tell you whether something's going to be explosive or not. An organic chemist is going to go through and look at structures and say whether something's going to be explosive or not. Okay? So slightly different spins on the same topic. Okay? We'd go through and do that with bases also, but we are now done. So I will go ahead and stop.